Welcome! Today I will show how threads are used in a TIBCO streaming application to process tuples and improve performance. A region is defined by the operators that, when processing a tuple, cannot also be processing a second tuple. A container has one top-level region, and each region comes with a transaction, a module thread, and an asynchronous queue called the parallel sequence queue to receive inputs when the module is busy. The simplest streaming application has one container, the default container, and only one module thread. A thread can only take advantage of a single CPU's worth of processing power. To make use of additional CPUs and run faster, explicitly add concurrency. The terms multi-threaded, concurrent, running in a parallel region, and asynchronous all mean the same thing in event flow, that multiple tuples are processed at the same time. Adding concurrency to any element creates a new region at that point, and if it's a module element, the region encompasses all elements within that module. When not marked concurrent, this means that everything running within a module runs in the same region as the containing application, and blocks a second tuple from processing at any level in the region. Region threads are not the only threads in a streaming application. For application sizing, it's the busy threads that determine how many CPUs you need to run the application. The simplest application will have 50 to 55 threads, as shown by JConsole, JVisualVM, or a JStack dump. Fortunately, most threads are intermittent and take up little CPU. When designing your application to take advantage of the CPU power of your system, reserve some CPU capacity for handling OS maintenance tasks and input-output. Some threads appear constantly busy 100% of the time, but instead release and defer the CPU to any other thread. These can be ignored and don't actually count as taking up a CPU. For example, we see the attached listener, event bus monitor, native log bridge reader, reference handler, RMI TCP accept, RMA TCP connection, runtime, and the signal dispatcher. Also, any thread where the thread stack involves NET or TCP. In an oversubscribed system, there are more individual threads working on data than there are CPU elements. Threads timeshare a CPU by context switching, also called CPU contention. Simply adding concurrency to a streaming application may easily oversubscribe a system. All the operators in a region run in a transaction, and the platform ensures there is only one transaction within that region at a time. It is a transaction that blocks any other threads from using the region's operators. The exceptions to this are what goes on inside an adapter and query tables, which may be accessed any time for reading and writing by any thread. The access is done in the thread of the calling query operator. The singular transaction for the region maintains consistency in transactional memory, JMS, JDBC, and any exception handling. Now let's look at how concurrency behaves. We typically add concurrency to module operators. Making single operators concurrent doesn't provide much benefit for the added queue cost. Anytime a tuple enters an operator and does not automatically leave that operator as the next step, completes the tuple. And if there are no side effects from that tuple yet to be handled, the transaction is completed and the region becomes idle and ready for the next tuple. Examples of completing the tuple are: the tuple enters an output stream, the tuple enters an output adapter, the tuple enters a query that returns no results, the tuple enters an aggregate that does not emit. Some common side effects that prevent the transaction from closing are: the tuple has yet to emit from a split operator port, the tuple caused one or more tuples to emit from a query operator, the tuple caused one or more tuples to emit from an aggregate operator. The tuple entered an output stream with a synchronous container connection. In all these cases, there are remaining actions directly caused by the active tuple that must be resolved before that active tuple is considered complete. After the prior tuple is complete, the next tuple into the event flow region may be from any input, not just what you consider the main input. The queued tuples are kept in arrival order by the parallel sequence queue. But this order is by strict arrival into the queue, not necessarily the order you'd prefer. In all cases, if a module can take input from more than one source, no order guarantees are made between different sources. So now we know why to add concurrency, which is to make more use of available CPUs. The next question is where to add concurrency. Typically, developers add concurrency and multiplicity on a single module element to make it spread the work across multiple threads, which, if there are more CPUs available, result in parallel work. Using multiplicity is vertical parallelism. This allows tuples to pass each other and emit in a different order than they entered. Alternatively, you may add concurrency with horizontal parallelism by chaining modules and making each module in the sequence concurrent. This is like an assembly line. This will split the work of the application into smaller chunks, which make use of more CPU cores in parallel. Each step may be performed on different data tuples at the same time. This keeps all tuples in the order received without letting them pass each other. Note that as shown here, this moves tuples from the parent queue to the child queue, back to the parent queue into the next child queue, back into the parent queue, and so on. Since adding concurrency adds queues, take some care to minimize queue growth. You may have seen in the engine log the, quote, queue name expanding, end quote, warning. This means that for a period of time that region is taking more tuples into its queue than can be removed by its module thread and the queue handler thread. Prevent most queuing by making sure each downstream region can do its work a little faster than the upstream region, so is always idle and ready when the next tuple arrives. The queue manager thread is a single thread, so can block if there's too little CPU available. Blocking on the queue manager thread for over 1 second, by default, is what triggers the queue to expand. Large payloads do not take queue memory directly since they are passed by reference, but large payloads tend to stick around in memory, which uses more CPU by the Java garbage collector, particularly as memory use approaches the maximum heap allocation. The best pattern for truly large payloads is to write the payload to a query table, then pass the primary key in the tuple. At each point where some payload data is needed, query it from the table and write your results back into the table for pickup in following regions or for output. Looking back at the vertical and horizontal parallelism examples, both introduce a number of queues in which copies of the same tuple may hang around until replaced by later data. If it is a large tuple, that may amount to a lot of occupied memory. Passing a primary key from a query table row in the queued tuple instead of the complete payload will reduce the impact of these copies. You should now have a better idea how threads are used in your application and a good understanding of when to add concurrency to make the best use of your available CPUs. I look forward to speaking to you again in our other videos. Also, see our community site. And of course, don't forget to subscribe to our channel.